Let's describe an interstellar journey of a spaceship from the Earth to a star. I will not take into account the acceleration and the deceleration of the spaceship after its launch and its landing, a very important point if you want to do a safe landing on the star, for example. The situation is this. An observer on the Earth sees the spaceship approaching the star, while an astronaut on the spaceship going to the star sees the star approaching and the Earth getting far from him. Due to the relativistic effect, the distance Earth-star measured on the spaceship contracts, so that the astronaut has a shorter journey depending on the velocity of his spaceship. The astronaut, for example, sees this situation in which the star is nearer to the Earth, and the relationship between the distance Earth-star measured on the Earth and the distance Earth-star measured on the spaceship is this, in which gamma is the Lorentz factor. Length contraction in the spaceship reference is evident on this graph. Increasing the spaceship velocity, the distance to travel shortens. Instead, lowering the velocity, the journey to the star is longer, not only because the spaceship is lower, but also because the path to travel is longer due to the relativistic effect. To consider the direction of the movement and the time, space-time graphs can be used, in which the points represent events. This is the space-time in the S-reference of the Earth. This is the event of the launch of the spaceship, and this the event of the spaceship arrival to the star. And this is the spaceship world line. Varying the velocity of the spaceship, the arrival time varies. But there is no relativistic effect, as frame is in quiet, and in it we see the spaceship like a point which moves uniformly to the star along the x-axis. This is instead the space-time of the S-prime reference of the spaceship, which moves uniformly with the velocity v relative to the Earth reference shown in the other graph. This reference moves so that the relativistic effect should be taken into account. This is the spaceship and the astronaut world line. The astronaut, looking along the direction of the motion, along this direction, sees the star approaching to him until its arrival at the star. Due to the relativistic effect, the star distance is contracted. The distance of the star measured on the Earth is 1.5 light years, and the spaceship reaches it after 2.5 years. But in the S-prime reference, the astronaut measures 1.5 light years divided by the Lorentz factor, so he measures 1.2 light years and reaches the star after 2.5 years divided by the Lorentz factor, so he reaches the star only after 2 years. In the relativistic description, the constant of the motion is the displacement and not the distance and the time, like in the classical case. In the spaceship reference, the value of the square displacement from the spaceship arrival event to the launch event is 4, as well as in the Earth reference. Another useful way to describe the travel to a star is the Minkowski space that was obtained in the first video. It describes two inertial frames moving, one relatively to the other, with velocity v. The orthogonal axes of the Minkowski space, x and t, are those of the S-frame of the Earth, while the oblique axes x prime and t prime are those of the S prime frame. We put on the graph the event of the arrival of the spaceship to the star and adduce the velocity of the S prime frame to the velocity of the spaceship. Now, the S prime frame is the reference frame of the spaceship, and the x prime t prime axes are the coordinates of the reference frame of the astronaut. The star is 1.5 light years far from the Earth. The velocity of the spaceship is 0.6 c. So the personnel of the Earth will see the spaceship reaching the star after 2.5 years. But with the x prime and t prime axis, we see that the astronaut who stays on the spaceship at x prime equals 0, this is also the world line of the astronaut, will arrive to the star after only 2 years. We should use correctly the oblique coordinates. Now let's suppose that the astronaut on the star wants to come back to the Earth. On the Earth reference, the spaceship, which took 2.5 years to travel to the star at the same speed, will take other 2.5 years to come back to the Earth. From the launch at t equals 0 and the coming back of the spaceship, 5 years will pass. That's on the Earth reference. But what happens to the astronaut in this reference frame? Obtaining the Minkowski space construction, in the first video we considered the motion from left to right of the S prime frame. S and S prime joined at t equals 0, and then the S prime frame moved to the right. But to describe the spaceship return, we need a construction in which the movement of the S prime frame starts from the right and with velocity v reaches the S frame that stays in quiet. It is easy to get this. It is sufficient to change the sign of the velocity. So, let's vary the velocity of the s' frame, represented by the x' and t' axis, till the negative values. This is the position of the s' axis when the velocity is minus 0.6 c, that is the velocity during the spaceship return. The movement is correctly from the higher x values to the lower x values. In this part of the t' axis, the value of the time is negative, and this is because in its movement from right to left, s' passes through the s' frame after its starting and not at its starting. So to avoid this, we should change the time origin, putting it in this region. For example, at the instant when the s' frame reaches its velocity. I have shown that in this point there is the event of the spaceship return, and so to describe the situation we should shift the point of the meeting of the two inertial frames to this point. In this way, I changed the color of the spaceship reference axis. I put the origin of the t' axis here, at the launch of the spaceship on the star, 2 years after its launch from the Earth. We should pay attention that the axes of the spaceship reference are oblique, and consequently the coordinates of its points should be read as oblique coordinates. So in the Earth's reference, this point is 1.5, 2.5, while in the spaceship the point stays on the t' axis, so its oblique coordinates are 0, 2, and this point is 0, 4. There are no gaps or similar oddities. Simply we should correctly use the oblique coordinates. We see that the return journey takes 2 years. So, during his journey, the astronaut gets 4 years older. On the other hand, on the Earth, the spaceship takes 5 years to complete its journey, so that we are perfectly aware that the astronaut is 1 year younger than his colleagues who stay on the Earth. There is the famous twins paradox. But now we have no problem to say which of the two twins is younger. It is the description of the situation that generates confusion, making the reader think that the situation between the two twins is symmetrical, but it is not. Anyway, it carries us to this problem. If I see an object which comes towards me, am I moving or is the object that moves? If we are on a train, sometimes we get the sensation that we are moving, but instead is the train on the near rail that is moving. In relativity, to determine who is moving has strong implications on the length and the time measured on the different references, but the sensation is the same that in the classical case. Of course, we can find ways to determine who is moving and who is in quiet. For example, to look at the landscape or even to take an accelerometer on board.